Hi there, folks. Today we're looking at solving radical equations. And from our perspective, we're only going to solve radical equations from the perspective of square roots. When you get to Algebra 2, you'll get to do cube roots and fourth roots and fifth roots and all that fun stuff. But for right now, we're going to focus on square roots. And if you think about what a square root is as an operation, it's the reverse, it's the opposite of squaring something. 4 squared is 16. That's how we know that the square root of 16 is 4, all right? They're basically going backwards from one another. And so when we kind of think about that, that should tell us all we need to know about how to solve things that have square roots in them. So roots and exponents are essentially just inverse operations. They're doing the opposite operation. And so to undo the square root, we just square each side of the equation. All right, squares and square roots essentially cancel each other out. And if you kind of think about this, going back to our good buddy Irmdas, order of operations, I always write it this way for a couple different reasons, like the A and the S are stacked and the M and the D. One, it's because when we're doing order of operations, those things are tied. Addition and subtraction are tied in terms of order of operations. You don't necessarily do addition before subtraction. You got to go left to right when there's a tie, okay? Multiplication and division are tied. Exponents, roots are tied, all right? And the reason they're tied is because they're technically the same operation. And subtraction is a special version of addition. It's adding a negative. Division is a special version of multiplication. It's multiplying by a fraction. Roots are actually a special version of exponents. You'll get to explore that a little bit more in Algebra 2, all right? But they're technically the same operation. They're just special versions. And they're the version that undoes the other one, okay? We know that addition and subtraction cancel each other out. They undo one another because they're the same operation, but the opposite version of the same operation, okay? Multiplication, division, once again, they cancel each other out because they're inverse operations. They're the same operation, but the opposite version of that. And exponents and roots are the same thing. And so when you think about an exponent and a root, they're inverse operations. They cancel each other out. So if I have a square root, I can undo it by squaring each side of the equation. Likewise, you can probably figure out that to undo a cube root eventually, you're going to cube each side. To undo a fourth root, you'll raise each side to the fourth power, okay? And so the idea of looking at that root and saying, hey, if this is a square root, there's like a little 2 there, I can undo it by squaring each side. Just like to undo a plus 3, I would do a minus 3. To undo a plus 5, I would do a minus 5, okay? So we have to do the opposite operation, and we have to kind of match the numeric value. And it's the same kind of thing here. And so as we look at these, again, when you look at a square root, we don't see a number written there, but we know there's actually a little 2 written right here. And so the square root, it's a root involving an exponent of 2. It's undoing the exponent of 2. And so to get rid of the square root, I simply square each side of the equation. To get rid of a square root, I square each side. And whatever I do one side of an equation, I have to do the other side of an equation, okay? That's always going to be true, and that has always been true. Whatever you do to one side, I have to do the other side. And the idea here is if these are inverse operations, the square root and the square just cancel each other out. And so if that entire root cancels out with the exponent, the only thing I'm left with here is an x. Over on the other side, it literally says 4 to the second power, which is 16. Okay? If I look at the next one, same kind of thing. There's a little 2 here. I don't typically write it, but I know it's there. And so because there's a 2 there, I have to undo this by doing a 2 as my exponent. So to undo the square root, I'm going to square each side. Again, whatever I do to one side, I have to do the other side. And once again, the root and the exponent cancel each other out, so I'm just left with a y. Over here, it literally says 8 squared, which is 64. The next one, once again, there's a little 2 there. I'm not going to write it this time, all right? But to undo a root with a 2, I have to use an exponent with a 2, so I write to the second power. And what happens is the root and the exponent cancel each other out, so I'm left with a. Over here, negative 2 to the second power is a positive 4, okay? And underneath here, we see this little asterisk and says, hey, be sure to check your solutions. You notice I didn't put a box around one of these. Plug them back in. If you plug the 16 in over here, right here, when you plug a 16 in for this guy, the square root of 16 is a 4, so that one works, okay? If you look at the next one, you plug a 64 in. If you plug a 64 in here for y, the square root of 64 is an 8. That one works. But if you look at this guy, if you plug the 4 in here, what happens is the square root of 4 is actually a 2, not a negative 2. All right, and so this one doesn't actually work. The solution I got doesn't work at all. So I'm going to say that does not equal. This one has no solution. Okay, so we're going to say no solution for this one. All right, and what we've done here is we've done everything right, but the answer still doesn't work. We call this extraneous solutions, and it's very rare that we get these. We don't get these in every type of situation, but this is one of the places where we can get extraneous solutions. So you do have to plug your values back in, plug your solution back in to make sure it works. You can do everything right and still get an answer that doesn't work because it's an impossible situation. All right, we're trying to solve something that's impossible, and so it kind of gives us like this false positive where it looks like we have a solution, but the solution doesn't actually work. Okay, it's called extraneous. It's an extraneous solution. So this one's actually no solution. All right, make sure you plug these back in and check them. All right. So again, extraneous solutions, apparent solutions that do not satisfy the original equation. And essentially, that's just a fancy way of saying you do everything right, but the answer still doesn't work, okay? We did everything correctly. We followed all the right steps. We solved appropriately, but the answer still doesn't work because we were given an impossible situation, okay? And so if that solution doesn't work, then no solutions work. And here's the thing, we'll solve some more complicated ones down the road here that maybe we'll get more than one answer for, all right? And maybe one answer is extraneous and the other one's not. That's okay, all right? If none of the answers work, then we say no solutions, right? So make sure you plug it back in, check for extraneous solutions. Solving multi-step radical equations, you really don't need any of this. If you remember how to solve equations and how that works at its core, all right, you don't need any of this, okay? Let me talk about IRMDOS once again. Remember, when we are solving equations, we work backwards through order of operations, okay? And we undo the operations as we go. So when we're solving equations, we go backwards through order of operations. I undo addition and subtraction first. Then I undo multiplication and division. Then I undo exponents and roots. And then I undo inclusion symbols, okay? And the thing we have to recognize here is invisible parentheses. We've seen situations where there are parentheses that are implied before. One of the classic situations is something like this, like x plus 2 over 5 equals 3. In this situation, we undo the division first because technically the x plus 2 is in parentheses. And the reason for that is because that division sign, that operation of division is happening to the entire x plus 2. And so it's implied that there are parentheses around the x plus 2, which is why we undo the division, and then we undo what's in the parentheses. Then we undo that addition, that plus 2, okay? And so that idea of just working backwards through order of operations. And if you understand, hey, we got to undo parentheses last, then these are going to make a lot more sense, all right? So the memorization version of this is isolate the radical, undo the square root by squaring each side, and then solve what's left, okay? And so again, if you look at this thing, again, if you just work backwards sort of operations, I've got a root and I have addition. Well, according to order of operations, if I was actually simplifying, I would do the root and then the addition. But if I'm solving, I work backwards through order of operations. So I undo the addition first by subtracting 3 from each side. And now I undo the root by using an exponent. And since this is a square root, I have to use an exponent of 2. Again, the root and the exponent cancel each other out. Just like here, though, the plus 3 and the minus 3 cancel each other out. Okay, that's the whole point of why I'm doing this, all right, as I want to cancel out that thing so I can solve for x. And so I get x equals 36. And then make sure you plug it back in. And you don't have to do a very extensive, long thing off to the side. Just plug it in and say, okay, the square root of 36 is a 6, plus 3 is a 9. That one works, okay? Plug it in your head, all right? If it's too complicated to plug in your head, then take it off to the side and do a little bit of work. If I look at this one, I have a root and I have subtraction. So if I'm working backwards through order of operations, I want to undo the subtraction first. And to undo subtraction, I'm going to add the 2 to each side, okay? Once again, the whole point of that is the 2 and the minus 2 cancel each other out. And now I want to do the same thing with the root. To undo a square root, I'm going to use an exponent of 2. So I square each side. And again, the root and the exponent cancel out, so I'm just left with m. Over here, I've got 49. And once again, plug it back in. The square root of 49 is a 7. Minus 2 is a 5, so that one works. Okay? If I look at this one, same kind of thing. I have multiplication, I have a root. It's times 6 and a square root. See, it's the square root of x and then times 6. When I work backwards sort of operations, I have to undo the multiplication first. So to undo multiplying by a 6, I'm going to divide each side by a 6. Over here, that gives me a 3. And now to undo the square root, I'm going to square each side. So I end up with x equals a positive 9. And again, plug it back in. The square root of 9 is a 3 times 6. It does give me an 18. All right. But again, we're just working backwards sort of operations. And if you look back up at this thing, yeah, we isolated the radical. We got rid of everything first and then undid the radical. All right. We still haven't got to the really complicated ones where we have stuff left over to continue to solve. But again, if we're just working backwards sort of operations, this thing kind of takes care of itself. Okay. We work backwards sort of operations. We undo operations as we go. If I look at the next one, again, if I'm working backwards sort of operations, I've got a times 2, I've got a plus 5, and I've got a square root. So working backwards sort of operations, I want to undo the addition and subtraction first. So I'm going to undo the addition by subtracting 5 from each side. Okay? I'm working backwards sort of operations just like I've always done with every other equation ever. And now once again, I have multiplication and I have a root. Working backwards sort of operations, I undo the multiplication next. And now to undo the square root, I'm going to square each side. Okay, it's a root with a little 2, so I have to use an exponent of 2. The root and the square root and the square cancel each other out. And over here, 10 squared is 100. And again, plug it back in. Square root of 100 is a 10, times 2 is a 20, plus 5 is a 25. That one works. Okay? If I look at the next one, same kind of thing. I have subtraction, I have multiplication. I want to undo the subtraction first because I'm working backwards sort of operations. So I undo addition and subtraction. Now I undo the multiplication. So I'm going to divide each side by 11. And now I'm going to undo the root by squaring each side. Okay, so just working backwards sort of operations, undoing the operations as I go. This one, same kind of thing. To undo the addition, I'd use subtraction, so I undo the addition first. That gives me a negative 2. That is terrible looking. Now I undo the multiplication with division. And now I undo the root by doing an exponent, so I raise each side to the second power. And I get r equals a 1. And again, plug it back in. The square root of 1 is a 1, times 2 is a 2, plus 7 is a 9. But wait a minute, it's supposed to equal a 5. And so if you're looking at that going, okay, wait, I must have messed something up. Let me take it off to the side. We didn't mess anything up. Plug this in. Ready? Square root of 1 is a 1. So that's 2 plus 7 equals 5. That's 9 equals 5. And if you're looking at this going, well, that doesn't equal. What's going on here? Well, this is an extraneous solution. The r can't equal to the 1. It doesn't work, which means I don't have any other answers here. The answer is really no solution, okay? This one is an impossible situation. And you might have recognized that, if you take the square root of something, we never get negatives when we take the square root of things, okay? We can't take the square root of a negative yet. And so when we try to take the square root of a negative, we end up with a no solution type of situation. Well, it's the same thing here. I had the square root equals a negative. That tells me that this thing is going to be no solution without even going any further. But make sure the square root's by itself before you make that judgment call, okay? So sometimes we can identify an extraneous solution before we get there. And if you look right here, this step, you can identify it right there in this step. As soon as I see the square root equals a negative, that's an impossible situation. So any answer I get is not going to work. Okay? You can't always identify extraneous solutions ahead of time, but that's one situation where you can. Okay? If I look at the next one, this is where it becomes a little bit trickier in terms of working backwards through order of operations. And it's because there are parentheses here that we don't actually have drawn. The parentheses are implied. okay? And parentheses are implied anytime we're doing an operation to an entire string of values, okay? So whenever there's an operation happening to a bunch of stuff all at once, there are parentheses that are implied. And when you look at this one, I have the square root, and that square root is applied to the entire x plus 5, which means there's technically parentheses around this x plus 5, okay? And this dictates how I have to approach undoing order of operations. See, because that x plus 5 is in parentheses, it means that's the last thing that I'll undo, okay? So again, working backwards through order of operations, I'm going to undo the plus 3 by subtracting 3 from each side. Again, there are parentheses technically around this x plus 5. So now instead of undoing the addition that's under there, instead of undoing the plus 5, I'm actually going to undo the root next. And the reason for that is because the x plus 5 is in parentheses, which means I have to undo it last, okay? And so here, to undo the square root, I square each side. The root and the exponent cancel each other out. So I'm just left with the x plus 5. I'm just left with whatever the radicand is, okay? See, essentially now what I'm left with is I'm left with whatever was in the parentheses, okay? And so since I'm left with what was in the parentheses, I can now undo what was in the parentheses by subtracting 5 from each side. And so that's the idea when you're looking at this thing in terms of that idea of isolating the radical. That's why you isolate the radical and then undo the radical and then undo what's left underneath the radical, okay? It's because what's left underneath is technically in parentheses. And if we're working backwards through order of operations, we have to undo the parentheses last, okay? I forgot to plug this one back in. Let's plug it back in. 139 plus 5 is 144. The square root of that is a 12, plus 3 is a 15, okay? If I look at this guy, once again, there are parentheses that are implied here. So this entire thing is in parentheses, which means I can't undo the times 2 or the plus 3 because it's in parentheses. I have to undo everything else before I undo parentheses. So I'm going to undo the radical first by squaring each side. Again, the root and the exponent cancel each other out. So we never have to square any of the stuff that's underneath there, okay? As soon as we try to square this, it cancels out with the radical, and I'm just left with the 2x plus 3. Over here, sorry, I forgot to put the little squared. Over here, I square this and I get a 9. Now I'm left with what's in the parentheses. Inside the parentheses, I start working backwards through order of operations again. So I work backwards through order of operations by subtracting the 3 from each side and then dividing by the 2. Okay? So if you want to think of it as, hey, I have to isolate the radical and then get rid of the radical and then undo what's left underneath, that's fine. But just remember, it's just because there are parentheses. We're still just working backwards through order of operations. And if I plug this guy back in, 2 times 3 is a 6, plus 3 is a 9. The square root of that is a 3, so that one works. Okay? If I look at this one, once again, there are parentheses here around the x minus 5, so that's the last thing that I'll undo. The last step will be to add to 5, okay? That's the last thing I can do. So now, outside of that, I have addition, I have multiplication, I have a square root. Working backwards sort of operations, I'm going to subtract the 4 from each side, so I'm going to undo the addition. Then I'm going to undo the multiplication by dividing each side by 3. Again, because there are parentheses around this x minus 5. Now I'm going to square each side. The root and the exponent cancel out. Sorry, I forgot to put the little 2. And now I add the 5 to each side. Sorry, that is not the color I typically use for adding things to each side. There we go. My trusty red. So I get x equals 6. And once again, plug it back in. 6 minus 5 is a 1. The square root of 1 is a 1. Times 3 is a 3. Plus 4 is a 7. But it's supposed to equal a 1. This is an extraneous solution. And you might have caught it in there as we were working our way through. You might have seen the moment that you could have identified this. I had the square root of something equals a negative 1. That was no good. So right here at this step, as soon as I see the square root equals a negative, I know that's not going to work, okay? We can't always identify extraneous solutions ahead of time, all right? But when we can, we want to take a little bit of that shortcut, okay? Take that little bit off. So once again, to undo the square root, I square each side, and now I just apply the same rules I've always applied, that idea of reverse engineering, working backwards through order of operations and undoing the operations as I go.